I'll not get your face in it, I'll just get for copyright and stuff.
Let me turn the camera over. Shall we stop?
Bliat.
Move his camera, shall we?
You have 2 leaves. What's the inner leaf in a 1950s house?
Brick.
Brick, thank you. 2 leaves of brickwork, okay. There may or may not be insulation in the cavity, because it's a 1950s house. It certainly wouldn't have been built with insulation, but insulation may have been added since then, yes. Then above that, you've got the window, yes. And above that, you've got the head of the wall. Okay. Resting on that, what's the structure of a roof of a 1950 house? Is it a truss, king post, or purlin?
Big king post.
Divvies.
Trust.
Divvy.
Helen.
Thank you. By process of elimination, king post is for large buildings. You find that in medieval barns. This is where I find you was born in a barn.
Oh, my dad's a farmer.
So yeah.
So yeah, he like, I've actually took a photo of a king post roof. How sad's that? I actually took a photo of it.
Depends what
Like,
colours available.
I've actually
I
got it.
suppose if you weren't born in a barn, there's a fighting chance you was conceived in one. Don't worry, Jesus was born in a barn, so you're okay. Right, on top of the wall, we have
Nice roof.
the ceiling joists, and that will extend. Yes, if you look at the building here, it's pitched roof. So the pitched roof, half the load goes one way, half the load goes the other way. So basically, the joists, you'll take the load of the joists, ceiling joists, halfway along the building, right? Okay, so that's the centre line of the building. The next thing to consider is that there'll be rafters. So the rafters will be up here. And the rafters, because it's purlin, will be resting on a purlin. Okay.
Yeah, I get that.
Underneath the ceiling joist will be plasterboard. Resting in the ceiling joist will be insulation. Yes?
Yeah.
Okay. Inner face of the building will have plaster. Notice that the joists span parallel to this wall, so the floor is not supported by this. So do you need the floor loading for this part of the calculation?
No.
No, you don't. Okay. On top of the roof, the rafter is what?
Tiles.
Tiles, battens, and Sarkenfeld. I gave you a unified one for this. I wasn't going to calculate it in total. So I calculated for tiles, battens, and Sarkenfeld and gave you a value of 0.7 kilonewtons per metre squared. It's actually, I calculated 0.698, but I rounded it because, you know, I'm not fussed too much about that part. Provide you all with the same hymn sheet there. Okay? That's to do with Jesus as well, isn't it? Yes. And the barns. Okay? So that's a global figure there per square metre. And then on top of that, there will be snow.
So is this because we're doing the maximum kind of thing? Like this is what
Yes.
could be, and then you've got to like put
Also, in the roof
Storage.
in the roof
The
space
roof
will be
space.
light storage. Okay, because people put all sorts of rubbish in the roof.
Christmas trees.
Christmas
etc.
trees. Actually, I've got most of the books up there, so I'm well and truly beating into my 1.6 limit state allowance. Furthermore, when I move around in my roof space, I'm a fairly substantial point load, so I'm very careful where I put my foot on the trusses and such like, because I don't want to sort of disappear through the roof into the floor below, because that will frighten the cat, something wicked. She's a nervous creature at the best of times. If I just suddenly appear through the ceiling, I think she'll run a mile. Okay, so that's what you're calculating, all that lot. Now, if you face the building, here's the beam. So this is the zone where the beam is, you will see a brickwork, window, roof, yeah? And you need to calculate the area of these things, or at least the loading. Now then, you've been given various values for loads and the building, the various values there. There's various ways of doing this. So, for example, you've been given a value for brickwork, which is 22 kilonewtons per cubic metre. However, each of those leaves is not a cubic metre, is it?
No.
How wide is a leaf?
For
160.
100. A leaf of...
A leaf of brickwork. What's the width of a brick?
102.
102.5. In actually, this was an imperial building, it'd be 4.5 inches. But we won't worry too much about that. You can do it 4.5 inches if you wish, or you can do it 102.5. I'm chilled either way.
Would you not do both sides like that?
Both inner and outer
Yeah,
will be that.
yeah.
We don't know what the width of the cavity is, but I can assure you that cavities have got bigger over the years as we stuff more insulation in them. Okay? But that's not a big thing other than the calculation of the insulation, but insulation isn't a big load. Now then, if you've got a 1 metre by 1 metre cube brickwork, but you've only got 102, so what you do is you work out okay, we just want this slice of brickwork out of the 1 metre, don't we? Yeah?
Let's break out the volume of it.
So and then we've got the volume of the brickwork, but if we know one of the parameters, what we can do is to do 22 times 0.1025, and that will give you a result It's 2.26 kilonewtons per metre squared of brickwork, yes?
So how much force is then pushed from that bit of brickwork?
That's how much force. That's how much force is being pushed from a 1 metre by 1 metre by 0.1025 or 102.5 millimetres slice of brickwork. In other words, that's how much force for every square metre of the outer leaf. We now measure how much brickwork is up there. With this, you probably need a computer. So go to CAD and measure the size of brick. So you say, okay, what's how much brickwork is there?
So the length and the height times.
The length and the height of that brickwork.
So you calculate the area of it.
You calculate the area of the brickwork. So
That's what we were doing earlier.
I'll give it a global figure. I'll just say area, and this is just made up, is 2.3 multiplied by 0.9. So we've got that. So that's not the right answer, by the way. So that's 2.07 square metres of brickwork, which means the total weight of brickwork for one leaf is 2.26 times 2.07 equals 4.68 kilonewtons.
So is that all the brickwork then?
That's the brickwork for one leaf. We've got 2 leaves of brickwork, haven't we? So we multiply that by 2.
Sorry, where's the second leaf of brickwork?
Because it's like you got brickwork then cavity.
Oh, right.
Yeah.
Yeah.
What, do you have to work out all the things inside?
All the loads, every load, yes.
Mm.
So I've got 2 litres of brickwork, so I times that by 2, and that's 9.36.
It's better setting a table out or something like that.
Yes,
So-
that's a good idea. Kilonewtons. And then you multiply that to the limit state, 9.36, multiplied by 1.4, because it's a dead load, it's a structural load, so we're just calculating for the building degrading. So it's 9.36 times 1.4 equals 13.10 kilonewtons, and that's the load of the brickwork on that beam. Divide that by the length of the beam, gives you the UDL. Divided by 2 gives you the reactions, okay? But you add all the forces together before you do that, okay?
And that's just for the brickwork.
That's
So
just
we've
for
got
the
to do
brickwork.
those
So you've got
notes.
to do that for like everything, like.
You've got to do that for everything, like.
And then you add them all up together,
Add them all together. and
times
you've
it
got
by
the total load.
1.6
Well,
or
no.
1.4.
Already done that.
No, you've done that already.
Oh, in that. Alright, yeah.
For the snow loading, you multiply by 1.6. For the roof light load in the roof space, 1.6. Everything else multiplied by 1.4.
Right, yeah.
What's this for here again for? Is that just one
That's
brick?
just a brick.
Right.
That's a lump of brickwork, 1 metre by 1 metre by 1 metre. Yes, because you're given a figure of a lump of brickwork, 1 metre by 1 metre by 1 metre. And you do that with everything else. You do that with the timber. The timber's a tricky one because you will have the joists
But that was a tricky one.
and the rafters. That was the easy one. Okay? You have to calculate.
How many there are? Like
You have to
above-
calculate how many there are within this distance of the roof. So if it's if it's the length of the beam, so it's 2.3 metres wide beam, and the joists are at 450 millimetre centres. So that's 2.3 divided by 0.45 equals 5 joists and 5 rafters in that distance. So what you do is you calculate the size of the ceiling joist.
Just the length, not the width as well. just
You
the
would
length.
calculate it all because you're given a figure of 6 kilonewtons per cubic metre. So you have to do cubic metre again, so it's length, height, width. And then you multiply length, height, width by kilonewtons per cubic metre, and that will give you kilonewtons. And then you multiply that by
How many?
5 or whatever, and then multiply that by 1.4. For this one, for the roof, the distance you use is the pitch distance, yeah? Not the, okay? And this distance here, this is about 5 metres, so it's going to be around about 2.5 metres to the centre line of the building, okay? So use that distance for calculating the rafters, and that distance for calculating the snow, and that distance for the roof finish. Okay? And you just work sequentially all through that, taking the different values, and your objective is to find the total load on that beam. Once you find the total load, so divide that load by 2, you've got the reactions, which means you've probably got the shear. Okay? And if you divide it by the length of the beam, you've got the UDR, so you're in a position to calculate the bending moment.
Why would you need to do that?
You need to find the shear to make sure the beam isn't going to fail in shear.
Right.
You need to find the bending moment, so you're actually in a position to calculate the section modulus and find out which size of beam you need to use.
And these go in our this goes in our coursework.
This is all part of the coursework. You do the calculations,
Yeah.
then the beam calculation, and then you write a report stating all the assumptions you make, because there are assumptions made here which you have to make to get this to work. For example, you are assuming...
So you're explaining the calculations in your report?
You don't explain the calculations so much as you explain the assumptions that underlie the calculations. So what size of beams did you assume? What size of brick, did you assume it was metric or imperial brick? Or what size brick did you assume? Yeah? Because a 4.5 inch brick is not the same as a 100 in a metric brick. Okay? For this beam here, it's relatively straightforward. The main problem is the support. Over and above it, as you can see, the floors run parallel to this wall. So the beam here is not really supporting anything in the way of floor. The main thing the beam is supporting is this wall here. Now, in 1950s houses, the walls are often what's called clay pots, built directly off the floorboard. There are clay pots. Ellison Building is of the same era and actually has clay pots walls. Many of the older walls, like that wall there, are basically clay, look like bricks arrangements, but they're the size of a block and they're hollow. I would suggest for this, don't worry too much about the nature, just design it for brickwork with plaster each side. You will overload the beam slightly. It'll be slightly heavier than it actually is, but it means that beam will be well within parameters. The beam will actually work very efficiently. But the main problem here is you need to find a very small beam to fit into that gap.
I thought the beam was there.
Yeah, so did I.
Hey, you're not doing that one.
Oh, you're not doing that one?
No,
It's there.
Right,
this one here.
right, okay.
Yeah, that's knocking 2 bedrooms into one.
No, I mean, on that floor, I thought it was there.
No, it's this
So
one here.
then
We're taking this one out.
We've got to do the same again for this one as well.
Yeah, so
That's
it's,
the one I've just been discussing.
yeah.
So,
I've just discussed this one here. This is this one here. This is the second one you have to do. And I'm just explaining the quirks there. There's not an awful lot of load in that beam other than that brick wall. It may be that you find you make a surprising recommendation there, but we'll see what load you come up with, what you actually work out.
The roof doesn't apply to that.
Do you think the roof applies to that?
No, because the roof would apply to that one there.
The roof doesn't apply to this one because the roof is being supported by these walls, isn't it? Yes?
What about the joists? Oh, the joists are running that way, so no.
Yeah, look.
They're not touching the wall.
Yeah, see which way the joists are running?
Yeah.
That makes a big difference to these calculations.
So it is just the brickwork and the
Is it-
plaster and then the storage and stuff in it.
For this one,
Yeah.
it's brickwork and plaster because the loads are supported by the floor and the floors have been supported here and here.
Yeah.
Okay? That's the walls supporting the floor. So any beam going across there is only supporting, that's the main walls there. Beam there, it's just supporting the brickwork there. Okay?
So beam 1 is the brickwork, the plaster, the windows, roof,
Everything.
Everything, yeah. And beam 2 is the brickwork above the beam on the ground floor and the upper floor brickwork.
Right.
Well, we'll call it brickwork. We know it's clay pots.
Alright.